Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whit Roy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Welcome to this audiobook for Part 1 of NZS 3000 to 2007, also known as the wiring rules. Before we begin, I want to be very clear, this audiobook does not replace the standard, and it must not be used instead of the official wording. When you do real electrical work, or when you sit an EWRB exam, you must use the exact text of the standard itself. My goal here is simple: to explain Part 1 in plain spoken language so you can listen, follow along easily, and understand the meaning behind each clause, even when you're driving or not reading the document. Everything you hear is based directly on the original 2007 standard. No rules are added, nothing changed, only rewritten so it's easier to understand. Alright, let's get started. Part 1: Scope, Application and Fundamental Principles. Section 1.1 Scope explains what Part 1 of NZS 3000 covers. Part 1 deals with the broad safety rules that apply to electrical installations. It lays out the high-level requirements, the essential things an installation must achieve so people, property, and livestock stay safe. These principles apply to every electrical installation covered by the standard. They apply no matter whether you are building a new installation, altering an old one, adding onto something, or repairing existing work. So think of Section 1.1 as the big picture rules. What the installation must achieve to be safe during normal use, during faults, and in any expected environmental conditions. Section 1.2 Application explains where Part 1 applies. Part 1 applies to all electrical installations covered by the standard unless a specific clause says otherwise. This includes new work, additions, alterations, and repairs. The key idea is that anyone designing, installing, testing, or verifying an installation must follow the safety principles set out in this part. Nothing in this section replaces any legal obligations under other regulations or laws. It simply tells you how Part 1 fits into the overall requirements for electrical safety. Section 1.3 Reference Documents tells you that the standard refers to other documents, such as equipment standards or installation standards, that support the rules in NZS 3000. These reference documents help explain how to select equipment, how circuits should be arranged, how testing is done, and how safety requirements are met. The important thing to remember is this: when the standard refers to another document, that reference document becomes part of the requirement, but only for the specific clause where it is mentioned. So you only need to use the reference documents where the standard tells you to. Section 1.4 Definitions. 1.4.1 Application of definitions. These definitions help us understand how certain words are used throughout the standard. Think of this section as the standard's own dictionary. Whenever the standard uses one of these terms, it is using the specific meaning listed here, not the everyday meaning. I will now explain each definition in simple spoken terms. 1.4.2 Accessible, readily. Something is considered readily accessible when it can be reached quickly without climbing over objects, removing obstructions, standing on a chair, or using a movable ladder. It must not be more than 2.0 meters above the ground, floor, or platform. 1.4.3 Accessory. An accessory is any device such as a switch, fuse, plug, socket outlet, lamp holder, fitting, adapter, or ceiling rose, used with wiring, luminaires, switchboards, or appliances. It does not include lamps, luminaires, appliances, or the switchboard itself. 1.4.4 Active or active conductor. An active conductor is any conductor that is kept at a potential difference from the neutral or earthed conductor. If the system does not have a neutral or an earthed conductor, then all conductors are considered active. 1.4.5 Aerial conductor. An aerial conductor is any stranded conductor, including aerial bundled conductors, that is supported by insulators or purpose-designed fittings above the ground and directly exposed to the weather. 1.4.6 Appliance. An appliance is any consuming device, other than a lamp, where electricity is converted into heat, motion, or another form of energy, or where the electrical characteristics of the electricity are substantially changed. 1.4.7 Appliance. Fixed. A fixed appliance is one that is fastened to a support or is otherwise secured in a specific location. 1.4.8 Appliance. Handheld. A handheld appliance is a portable appliance designed to be held in the hand during normal use, with any motor forming an integral part of the appliance. 1.4.9 Appliance. Portable. A portable appliance is one that is moved while operating, or one that can easily be moved from one place to another while still connected to the supply. Clause 1.4.10 Appliance. Stationary. A stationary appliance is either a fixed appliance, or an appliance that weighs more than 18 kilograms and does not have a carrying handle. Clause 1.4.11 Area. Hazardous. A hazardous area is a location where an explosive atmosphere is present, or may reasonably be expected to be present, in quantities that require special precautions for the construction, installation, and use of equipment. Clause 1.4.12 Arm's reach. Arm's reach is the zone extending from any point on a surface where a person normally stands or moves, to the furthest distance the person can reach with the hand in any direction, without using anything for assistance such as tools or a ladder. Clause 1.4.13 Authority. Regulatory. A regulatory authority is a government agency responsible for the relevant legislation and how that legislation is applied. Clause 1.4.14 Authorized person. An authorized person is either the person in charge of the premises, a licensed electrical contractor, an electrician, or another person appointed or selected by the person in charge to carry out duties on the premises. Clause 1.4.15 Available. Readily. Something is readily available when it can be reached for inspection, maintenance, or repairs without needing to dismantle cupboards, benches, structural parts, or similar. Clause 1.4.16 Barrier. A barrier is a part that provides basic protection from any usual direction a person might approach from. This definition also refers to basic insulation in Clause 1.4.60 and basic protection in Clause 1.4.77. Clause 1.4.17 Cable. A cable may be a single cable core or two or more cable cores laid together, with or without fillers, reinforcements, or protective coverings. Clause 1.4.18 Cable. Armored. An armored cable is a cable wrapped with metal, usually tapes or wires, mainly to provide mechanical protection. Clause 1.4.19 Cable core. A cable core is a conductor along with its insulation, but does not include any mechanical protective covering. Clause 1.4.20 Cable. Flexible. A flexible cable is one whose conductors, insulation, and covering provide flexibility. Clause 1.4.21 Cable. Mineral insulated metal sheath, MIMS. This type of cable uses compressed powdered mineral insulation enclosed in solid drawn metal sheathing. It may be single core or multi-core. Clause 1.4.22 Cable. Neutral screened. A neutral screened cable consists of one or more cores laid together, with or without fillers, surrounded by a concentric wire outer conductor, and protected by an insulating sheath. Clause 1.4.23 Cable. Sheathed. A sheathed cable has one or more cores surrounded by a sheath. Clause 1.4.24 Ceiling. Suspended. A suspended ceiling, as described in AS NZS 2785, is a ceiling system hung below the floor or roof above. Clause 1.4.25 Circuit. A circuit includes live conductors, protective conductors if any, a protective device, and the associated switchgear, control gear, and accessories. Clause 1.4.26 Circuit breaker. A circuit breaker is a switch designed to open a circuit automatically when preset conditions occur such as overcurrent or undervoltage, or when operated by external control. Clause 1.4.27, Class 1 equipment. Class 1 equipment does not rely on basic insulation alone for protection. Accessible conductive parts are connected to the protective earthing conductor so they cannot become live if basic insulation fails. Clause 1.4.28, Class 2 equipment. Class 2 equipment also does not rely only on basic insulation. It uses double insulation or reinforced insulation and has no provision for protective earthing. It may be A. Insulation encased. B. Metal encased with double or reinforced insulation, or C. A combination of both types. Clause 1.4.29, Class 3 equipment. Class 3 equipment relies on SELV for protection and does not generate voltages higher than SELV. Clause 1.4.30, Competent person. A competent person is someone who has the training, qualifications, experience, or a combination of these, to perform the required task correctly. Clause 1.4.31, Conductor. A conductor is any material capable of conducting electricity. Clause 1.4.32, Conductor, bare. A bare conductor is a conductor without insulation or covering. Clause 1.4.33, Consumer's mains. Consumer's mains are the conductors between the point of supply and the building or structure where they terminate. Clause 1.4.34, Contact, direct. Direct contact means contact of a person or an animal with live parts. Clause 1.4.35, Contact, indirect. Indirect contact means contact of a person or an animal with an exposed conductive part that has become live under fault conditions. Clause 1.4.36, Cord, flexible. A flexible cord is a flexible cable consisting of one or more flexible conductors. Clause 1.4.37, Current, fault. Fault current is the current that flows in a circuit during a fault. Clause 1.4.38, Current, overload. Overload current is a current that is higher than the rated current of equipment or conductors, but not caused by a fault. Clause 1.4.39, Current, short circuit. Short circuit current is a current resulting from a short circuit fault. Clause 1.4.40, Damp situation. A damp situation is a location where moisture is present in an amount that is enough to affect the safety of electrical equipment installed there. Clause 1.4.41, Distribution board. A distribution board is a switchboard that supplies one or more final subcircuits. Clause 1.4.42, Duct. A duct is a closed raceway of rectangular or circular shape for housing conductors. Clause 1.4.43, Earthed. Earthed means connected to the general mass of Earth. Clause 1.4.44, Earth's situation. An earth situation is one in which exposed conductive parts are connected to the earthing system. Clause 1.4.45, Earth fault loop impedance. Earth fault loop impedance is the impedance of the earth fault current path, starting and ending at the point of the earth fault. This includes all active conductors, the protective earthing conductor, and the neutral conductor where relevant. Clause 1.4.46, Electrical equipment. Electrical equipment is any item used for purposes such as generation, conversion, transmission, distribution, or use of electrical energy. Clause 1.4.47, Electrical installation. An electrical installation includes any fixed appliances, wiring, switchgear, control gear, and accessories that use or distribute electricity in a building, structure, or premises. Clause 1.4.48, Electrical installation, domestic. A domestic electrical installation is one associated with a dwelling intended for residential purposes. Clause 1.4.49, Electrical installation, multiple. A multiple electrical installation is an installation where more than one consumer occupies parts of the same building. Clause 1.4.50, Electricity distributor. An electricity distributor is an organization responsible for the distribution of electricity through a distribution system. Clause 1.4.51 Enclosure. An enclosure is a part that provides protection of equipment against external influences, and provides protection against contact with live parts from any direction of access. Clause 1.4.52 Equipotential bonding. Equipotential bonding is the connection of conductive parts to keep them at substantially the same potential. Clause 1.4.52a Explosive atmosphere. An explosive atmosphere is a mixture with air, under normal atmospheric conditions, of flammable substances in the form of gas, vapor, mist, or dust, where combustion spreads after ignition. Clause 1.4.53 Exposed conductive part. An exposed conductive part is a conductive part of equipment that can be touched and that does not normally live, but may become live under fault conditions. Clause 1.4.54 Extraneous conductive part. An extraneous conductive part is a conductive part that is not part of an electrical installation but is able to introduce a potential, usually earth potential. Clause 1.4.55 Fault current limiter. A fault current limiter is a device intended to limit the prospective fault current to a preset value. Clause 1.4.56 Functional earthing, FE. Functional earthing is earthing required for correct operation of equipment, not mainly for safety. Clause 1.4.57 Fuse. A fuse is a device that opens a circuit by melting a conductor when current exceeds a set value for a long enough time. Clause 1.4.58 Installation coupler. An installation coupler is a device used to connect fixed wiring to equipment without using tools. Clause 1.4.59 Insulated. Insulated means separated from other conducting surfaces by a dielectric that is capable of withstanding the required voltage. Clause 1.4.60 Insulation system. An insulation system refers to basic insulation and supplementary insulation, or reinforced insulation. Clause 1.4.61 International Ingress Protection Classification, IP classification. The IP classification identifies the degree of protection provided by enclosures against the entry of solid foreign objects and moisture. Clause 1.4.62 Isolation, isolating function. Isolation is the function of disconnecting a circuit or equipment from every source of electrical energy to ensure safety. Clause 1.4.63 Live part. A live part is a conductor or conductive part intended to be energized in normal operation, including the neutral in certain systems. Clause 1.4.64 Luminaire, lighting fitting. A luminaire is an appliance designed to produce light, and to distribute, filter, or transform the light from one or more lamps. It also includes all parts needed to support or protect the lamp and to connect it to the supply. Clause 1.4.65 Main earthing conductor. The main earthing conductor connects the main earthing terminal to the earthing electrode. Clause 1.4.66 Multiple earthed neutral system, MEN system. An MEN system is one where the neutral is connected to earth at multiple points, including the installation's main earthing terminal. Clause 1.4.67 Neutral conductor or midwire. The neutral conductor is a conductor connected to the neutral point of a system and able to carry current under normal operating conditions. Clause 1.4.68 Obstacle. An obstacle is a part that reduces the likelihood of unintentional contact with live parts, but does not prevent deliberate access. Clause 1.4.69 Outbuilding. An outbuilding is any detached building that is associated with the main structure on a property. Clause 1.4.70 Overcurrent. Overcurrent is a current greater than the rated value of the equipment or conductor. It includes overload current and short-circuit current. Clause 1.4.71 Plug. A plug is a device attached to a flexible cord or cable, intended for insertion into a socket outlet. Clause 1.4.72 Point and wiring. A point is a termination of the fixed wiring for connection of current using equipment. Clause 1.4.73 Point of attachment. The point of attachment is the point where overhead consumers' mains are attached to a building or structure. Clause 1.4.74, Point of entry. The point of entry is the point where underground consumers' mains enter a building or structure. Clause 1.4.75, Point of supply. The point of supply is the point where electricity is supplied to the electrical installation by the electricity distributor. Clause 1.4.76, Protected extra low voltage, PELV. PELV is an extra low voltage system that is not electrically separated from Earth, but provides protection by using low voltage and other measures. Clause 1.4.77, Protection, Basic. Basic protection is protection against electric shock under normal conditions, by preventing direct contact with live parts. Clause 1.4.78, Protection, Fault. Fault protection is protection against electric shock in the event of a fault, by preventing indirect contact with exposed conductive parts that become live. Clause 1.4.79, Protective earthing conductor. A protective earthing conductor connects exposed conductive parts to the earthing system to safely carry fault current. Clause 1.4.80, Residual current device, RCD. An RCD is a device intended to automatically disconnect the supply when the residual current reaches a given value under certain conditions. Clause 1.4.81, Ripple-free DC. Ripple-free DC is direct current with ripple content not exceeding 0.1%. Clause 1.4.82, Safety service. A safety service is equipment that provides essential safety functions in an emergency, such as lighting, alarms, or fire protection systems. Clause 1.4.83, Separated extra low voltage, SELV. SELV is an extra low voltage system that is electrically separated from Earth and from other circuits, giving protection against electric shock. Clause 1.4.84, Service protective device. A service protective device is a protective device installed by the electricity distributor to protect the service conductors. Clause 1.4.84a, shall indicates a mandatory requirement of the standard. Clause 1.4.84b, should indicates a recommendation, not a mandatory requirement. Clause 1.4.85 Socket, cord extension. A cord extension socket is the socket outlet that is part of a cord extension set. Clause 1.4.86 Socket outlet. A socket outlet is a device fixed to the wiring of an electrical installation, intended to accept a plug. Clause 1.4.87 Source of supply. The source of supply is a transformer, generator, converter, or other supply equipment that provides electricity to an installation. Clause 1.4.88 Subcircuit. Final. A final subcircuit is the circuit that supplies directly to current-using equipment. Clause 1.4.89 Submains. Submains are conductors between the main switchboard and a distribution board. Clause 1.4.90 Substation. A substation is an assembly of equipment where voltage is transformed, or where switching or protection equipment is installed. Clause 1.4.91 Switchboard. A switchboard is an assembly of switchgear, control gear, bus bars, and associated equipment used to control, protect, and distribute electrical power. Clause 1.4.92 Switchboard. The main switchboard is the switchboard that contains the main switch or switches for the electrical installation. Clause 1.4.93 Switchgear. Switchgear includes switches, fuses, circuit breakers, and other equipment used for switching, controlling, and protecting electrical circuits. Clause 1.4.94 Touch current. Touch current is the electric current that flows through a human or animal body when touching parts that are not intended to be live. Clause 1.4.95 Touch voltage. Touch voltage is the voltage that appears between parts that can be touched at the same time by a person or an animal. Clause 1.4.96 Track system. A track system is a system with one or more conductors arranged for movable or repositionable luminaires or current-using equipment. Clause 1.4.97 Trunking cable. Cable trunking is a closed enclosure of rectangular or circular shape used for accommodating cables. Clause 1.4.98 Voltage. Voltage is the difference in electrical potential between 2 points. Clause 1.4.99 Wiring, catenary. Catenary wiring is wiring suspended between supports, usually using a supporting messenger wire. Clause 1.4.100 Wiring enclosure. A wiring enclosure is any enclosure intended to provide mechanical protection for wiring. Clause 1.4.101 Wiring equipment. Equipment wiring refers to wiring that forms part of electrical equipment, rather than part of the fixed installation. Clause 1.4.102 Wiring installation. Installation wiring is the wiring of an electrical installation, excluding equipment wiring and flexible cords. Clause 1.4.103 Wiring underground. Underground wiring is wiring installed below ground level, with mechanical protection and insulation suitable for that environment. All definitions from Clause 1.4.1 to Clause 1.4.103 are now fully completed. Section 1.5 Fundamental Principles. Clause 1.5.1 Protection against dangers and damage. Section 1.5 explains the core safety ideas behind the NZS 3000 wiring rules. These principles are the foundation of the entire standard. If you understand these ideas, the rest of the book becomes much easier to make sense of. Clause 1.5.1 looks at what we must protect people, animals, and property from. Electrical installations can create several kinds of danger, but the standard highlights 3 main risk areas. A. Shock current. Shock current is electricity passing through a person or an animal. There are 2 kinds of electric shock we must think about. Direct contact. This happens when someone touches a part that is meant to be live in normal service. For example, an exposed terminal or a damaged cable where the active conductor is visible. Indirect contact. This happens when someone touches metalwork that is not meant to be live, but it has become live because of a fault. A common example is the metal case of an appliance when the insulation has failed. Why is this important? Because electric shock can seriously injure or kill. To manage this risk, the standard brings in a whole range of protective measures such as insulation, barriers, earthing, RCD protection, and automatic disconnection of supply. All of these are there to prevent electric shock, or at least reduce the risk as much as possible. B. Excessive temperatures. The second danger is excessive temperature. Electricity can create heat, and if that heat is not controlled, it can burn people, damage equipment, or start a fire. Typical causes of excessive heat include cables overheating, loose terminations arcing, overloaded circuits, and luminaires or appliances getting too hot for the materials around them. Anyone designing or installing an electrical installation needs to make sure that people, materials, and equipment are protected from hot surfaces, hot components, arcs or sparks, and heat buildup in general. C. Explosive atmospheres. The third danger is explosive atmospheres. Some locations have flammable gas, vapor, or dust in the air. In these places, even a small spark can ignite the atmosphere and cause an explosion. Examples include fuel storage areas, grain silos, spray painting booths, and certain industrial environments. In these locations, the electrical equipment must be specially designed, selected, and installed so it does not ignite the surrounding atmosphere. Section 1.5 Fundamental Principles. Clause 1.5.2 Control and Isolation. Now we look at control and isolation. Every installation must allow the circuits to be controlled and isolated safely. Control is the everyday switching, turning things on or off in normal use. Isolation is more serious. Isolation means disconnecting a circuit or a piece of equipment from all live parts, so that someone can work on it safely. A few key ideas apply here. Depending on the system, isolation may also be required in the neutral conductor. An isolating device must never disconnect the earthing conductor or APEN conductor. Safety services, such as emergency lighting, must have their own separate control system, so that ordinary switching cannot accidentally turn the safety equipment off. The main point is this: safe isolation is essential for electricians and maintenance staff. If isolation is done incorrectly, it creates a serious electric shock hazard. Clause 1.5.3 Protection against electric shock. Clause 1.5.3.1 Scope. This clause explains what the standard expects for electric shock protection. Both types of shock must be prevented. Direct contact shock happens when someone touches parts that are live in normal service. Indirect contact shock happens when someone touches metalwork that is not meant to be live, but it becomes live because a fault has occurred. To meet this requirement, live parts must not be accessible in normal use, and exposed metal parts must not become live in normal operation or under a single fault. Clause 1.5.3.2 Methods of protection. The standard uses two layers of protection. A. Basic protection. Basic protection prevents contact with live parts during normal service. This is achieved through insulation on live parts, barriers, enclosures, or placing live parts out of easy reach. These measures are designed to prevent accidental contact under normal conditions. B. Fault protection. Fault protection deals with indirect contact, where a fault makes exposed metal become live. The main protective methods are earthing, bonding, and automatic disconnection of supply using devices such as fuses, MCBs, and RCDS. The aim is that if a fault occurs, the supply will disconnect quickly enough to prevent harm. Enhanced protection. Enhanced protection is a special approach used only in specific situations. Here, one protective method on its own provides protection both in normal use and under a single fault, but it must meet strict conditions in AS NZS 3000. Examples include SELV systems, such as 12-volt pull lights or shaver outlets, where the voltage is low enough to be safe in normal use and still safe if a fault occurs. Another example is double-insulated equipment, such as Class 2 tools or chargers. Even if one layer of insulation fails, the second layer maintains safety. PELV control circuits are another example, using low voltage that remains within safe limits even when referenced to earth. These methods give protection in normal operating conditions and during a single fault, which is why they are considered enhanced protection. Clause 1.5.4 Basic protection, protection against direct contact. Clause 1.5.4.1 General. This clause is still about protecting people from touching live parts during normal operation. Basic protection is all about preventing direct contact under normal conditions. Clause 1.5.4.2 Methods. Basic protection can be provided by several methods. These include insulation of live parts, barriers or enclosures, obstacles, and placing live parts outside arm's reach. One very important point is that RCD devices on their own do not count as basic protection. An RCD is an additional layer, not the primary method of protection. Clause 1.5.4.3 Protection by insulation. When insulation is used as the basic protection, it must fully cover the live parts. The insulation must be able to withstand mechanical stress, heat, chemicals, and normal electrical stress. Clause 1.5.4.4 Protection by barriers or enclosures. When barriers or enclosures provide the protection, they must give at least IP210 or 1pxxb in general locations. On horizontal surfaces that can easily be touched, the requirement is IP4X. These ratings prevent fingers or objects reaching live parts by accident. Clause 1.5.5 Fault protection, protection against indirect contact. Clause 1.5.5.1 General. This part deals with protection when a fault has caused exposed metal parts to become live. The requirement is that people must not be exposed to dangerous voltages if that happens. Throughout the installation, one or more suitable fault protection methods must be used, taking into account the external conditions in that particular location. Clause 1.5.5.2 Methods of protection. Fault protection may be provided by one or more of the following methods. A. Automatic disconnection of supply. The supply must disconnect automatically if a fault creates a dangerous touch voltage. The disconnection time must be fast enough to prevent harmful shock. The detailed limits are explained later in Clause 1.5.5.3. B. Limiting the touch current using Class 2 equipment or equivalent insulation. Here, we rely on double insulated or Class 2 equipment, or equipment with equivalent insulation. This prevents fault current passing through a person. More details are given in Clause 1.5.5.4. C. Protection by electrical separation. Some circuits can be made safe by being electrically separated from other circuits and from earth. This is explained further in Clause 1.5.5.5, with extra guidance in Clause 7.4. D. Limitation of fault current. In some cases, the fault current can be limited so that it remains below the level that would cause a dangerous shock. This method is less common in everyday installations. The standard points out that the most common method used in practice is automatic disconnection of supply. Clause 1.5.5.3, Protection by automatic disconnection of supply. A. General. Automatic disconnection aims to limit dangerous touch voltage on exposed metalwork. This is done in two steps. First, all exposed conductive parts must be connected to the protective earthing system. Second, a protective device must disconnect the supply quickly when a fault occurs. This method may also be needed for overcurrent protection under Clause 1.5.9 and Clause 2.5. The standard also points us to other areas for more detail. Clause 5.6 covers equipotential bonding. Section 2 explains the detailed disconnection requirements. Appendix B provides guidance on earth fault loop impedance. B. Touch voltage limits. If a fault occurs between a live part and exposed metal, and the touch voltage rises above 50 volts AC, or 120 volts ripple-free DC, then the protective device must disconnect the circuit within the required time. In certain special locations covered in Section 6 and Section 7, stricter touch voltage limits may apply. C. Earthing system impedance, earth fault loop impedance. The characteristics of the earthing system and the protective devices must ensure that disconnection happens within the required time, even when the fault occurs at the furthest point in the circuit. If the earth fault loop impedance is too high, the fuse or circuit breaker may not operate fast enough. Clause 5.7 and Appendix B provide more detail on this point. D. Disconnection times. For a 230/400 volt installation, the maximum disconnection times are as follows. 0.4 seconds for final sub-circuit supplying. Socket outlets rated up to 63 amperes. Handheld Class 1 equipment, or portable equipment that is intended to be moved by hand during use. 5 seconds for other circuits, such as submains, and circuits supplying fixed or stationary equipment. The standard notes that these times can vary when different voltages or installation conditions apply. E. Supplementary equipotential bonding. Supplementary bonding may be used to help reduce earth fault loop impedance so that the protective device disconnects within the required time. This involves bonding exposed conductive parts together and bonding them to the earthing system. It does not replace a CD protection or other safety devices. It simply helps ensure that those devices operate correctly. Clause 1.5.5.4, Protection by Class 2 equipment or equivalent insulation. A. General. Protection can also be achieved by using equipment that has double or reinforced insulation. This includes Class 2 equipment, equipment with basic insulation plus supplementary insulation, switchgear constructed to AS NZS 3439.1, or equipment where supplementary insulation is added over the basic insulation. If options 3 or 4 are used, the overall level of safety must still be equivalent to Class 2 insulation. The standard also points out that paints, varnishes, and similar surface coatings do not count as insulation. If there is a chance that double insulation could be damaged, then extra precautions may be needed. B. Constructional requirements. Where the protection relies on a covering or an enclosure, a few rules apply. Screws or bolts made of insulating material must not be used if replacing them with metal would reduce the insulation level. If a lid or door can be opened with a tool or a key, then any live parts behind it must still be protected by an insulating barrier that gives at least IPXXB or IP2X. That barrier must only be removable with a tool. Clause 1.5.5.5 Protection by electrical separation. Electrical separation is normally applied to individual circuits. The idea is to prevent electric shock by making sure the live parts of the separated circuit are not connected to earth, and the exposed metal parts belonging to that circuit are not connected to earth and not connected to exposed metalwork of any other circuit. Usually, a separated circuit supplies only one item of equipment, unless the extra conditions in Clause 7.4 are met. Clause 1.5.6 Additional protection by the use of RCD devices. RCD devices are used as extra protective measures. They are not intended to replace basic protection. Clause 1.5.6.1 Basic protection. On their own, RCD devices do not provide basic protection during normal operation. However, they can be added on top of the basic methods to give an additional level of safety. Clause 1.5.6.2 Fault protection. RCD devices are recognized as a method of fault protection. They operate by disconnecting the supply when the earth leakage current reaches a dangerous level. Clause 1.5.6.3 Where required. When RCD devices are used for fault protection, they must be able to disconnect the part of the circuit they protect at the set leakage value. The standard requires RCD protection as additional protection in places such as socket outlet circuits, lighting points, and handheld equipment, in certain wiring systems, in electric heating cables, in equipment used in damp locations, and in special installations listed in other reference standards. The key message is this. RCD devices cannot be the only protection under normal conditions, but they are essential in higher risk areas or where the standard specifically requires them. Clause 1.5.7 Basic and fault protection using extra low voltage, SELV and PELV. SELV and PELV systems can provide both basic protection and fault protection, but only when certain conditions are met. The first condition is the voltage limit. The system must be arranged so that it cannot exceed extra low voltage levels of 50 volts AC, or 120 volts ripple-free DC. The second condition is separation from other circuits. These circuits must be kept separate, both electrically and physically, from each other and from any higher voltage circuits. For SELV systems, the live parts must not be connected to earth or to any protective earthing system used by other circuits. For PELV systems, if a person can touch the live parts, the voltage must always remain within the limits allowed for that particular environment. In short, SELV and PELV systems stay safe because they operate at very low voltage and are kept carefully separated from higher voltage systems and, where required, from earth. Clause 1.5.8 Protection against thermal effects in normal service. This clause returns to heat and fire issues during normal operation. The installation must be arranged so that, during normal use, electrical equipment does not ignite flammable materials because of high temperature or arcing, and does not harm people or animals through heat or sparks. If equipment normally runs warm or hot, it must have enough ventilation so that temperatures remain within safe limits. Designers must also consider how increased temperature could affect nearby equipment or materials. The summary is simple. During normal use, the installation must not become a fire risk and any heat produced must be kept under control. Clause 1.5.8 Protection against thermal effects in normal service. This clause returns to heat and fire issues during normal operation. The installation must be arranged so that, during normal use, electrical equipment does not ignite flammable materials because of high temperature or arcing, and does not harm people or animals through heat or sparks. If equipment normally runs warm or hot, it must have enough ventilation so that temperatures remain within safe limits. Designers must also consider how increased temperature could affect nearby equipment or materials. The summary is simple: during normal use, the installation must not become a fire risk and any heat produced must be kept under control. Clause 1.5.9 Protection against overcurrent. Overcurrent can create high temperatures and mechanical stress in conductors. Protection against overcurrent can be achieved in two main ways. One method is automatic disconnection, where the supply is cut off before the current becomes dangerous. The second method is limiting the maximum current, so it cannot exceed a safe value or duration. In everyday language, fuses and circuit breakers must stop the installation from carrying more current than it is designed to handle. Clause 1.5.10 Protection against earth fault currents. Any earthing conductor, or any part of the installation that is expected to carry earth fault current, must be sized and installed so that it can safely carry that current without overheating. In simple terms, the earthing conductors must be strong enough to handle the worst realistic earth fault. The conductor must not overheat, melt, or become damaged when a high fault current flows. This clause makes sure the earthing system remains reliable during a fault, so protective devices can operate correctly and disconnect the supply safely. Clause 1.5.11 Protection against abnormal voltages. This clause deals with voltages that should not normally appear in the installation. The system must be protected against harmful voltages that may be caused by faults between circuits operating at different voltages, by voltages induced or appearing unexpectedly in conductors, or by harmful influence between different circuits or systems. Clause 1.5.11.2 Circuits at different voltages. Where circuits operate at different voltages, protection must be provided to prevent injury or damage if a fault occurs between them. This can be achieved by keeping the circuits well separated or by using suitable protective devices. Clause 1.5.11.3 Voltage disturbances and electromagnetic influences. This part notes that protection against overvoltages from events such as lightning or switching operations is not required under this clause itself. However, the standard does provide guidance on these matters in other sections. Clause 1.5.11.4 Voltage in unused conductors. Unused conductors can still pick up unwanted voltages. These conductors must be terminated and protected at both ends in the same manner as live conductors. Clause 1.5.11.5 Interaction between different circuits and installations. Protection is also required to prevent harmful effects caused by interaction between different electrical installations, between different circuits in the same installation, between electrical and non-electrical installations, and between the installation and the structure it occupies. The main idea is that different systems can interfere with one another, and the installation must be designed so that dangerous interaction or unexpected voltages do not occur. Clause 1.5.12 Protection against the spread of fire. This clause focuses on fire safety. The electrical installation must not start a fire or make an existing fire spread or become worse. Equipment must be selected and installed so that it does not block escape routes with flames, smoke, or hot gases, does not add to a fire or help it spread, does not become so hot that it ignites nearby materials, and does not interfere with people trying to escape. Other parts of the standard provide more detail, including requirements for switchboard locations and fire spread control. The short message is that electrical equipment must never worsen a fire or restrict evacuation. Clause 1.5.13 Protection against injury from mechanical movement. Some electrically driven equipment includes moving parts, and these can be dangerous if not properly controlled. Protection is required wherever maintenance staff may be exposed to mechanical hazards while working on the equipment, or where the equipment may need to be stopped quickly in an emergency to remove danger. The standard requires that there must be a means to disconnect or isolate the equipment so that maintenance and emergency stopping can be carried out safely. In simple terms, if something moves, there must be a safe way to shut it down. Clause 1.5.14 protection against external influences. This clause covers external influences, essentially, what the environment can do to the installation. The installation must be designed so that it can cope with the conditions that can reasonably be expected in the place where it is installed. These influences may include weather or water, dampness, corrosion, chemicals or salt, dust, steam or oil, temperature variations, vibration or mechanical impact, animals, plants, insects, seismic activity, explosive atmospheres, or any other influence that might reasonably affect the installation in normal service. The overall idea is simple: the installation must be built to handle the environment it lives in, whether that involves water, heat, dust, chemicals, animals, vibration, movement, or anything else that could realistically occur. Section 1.6, Design of an Electrical Installation, Clause 1.6.1, General. When you design an electrical installation, it must achieve 5 main objectives. First, it must protect people, animals, and property from harm. Second, it must work properly for whatever purpose it is intended to serve. Third, it must connect safely to the supply, whether that supply comes from the electricity distributor or another source, and it must remain safe during normal operation and during a fault. Fourth, it should minimize inconvenience when something goes wrong, so that one fault does not shut down the entire installation. And finally, the installation must allow safe operation, safe inspection, safe testing, and safe maintenance. In simple terms, a good installation design must be safe, must function as intended, must match the supply system, and must allow people to work on it safely later on. Clause 1.6.2, Supply Characteristics. Before you size cables or choose equipment, you first need to understand the supply that the installation will connect to. The standard lists several characteristics the designer must know. The first is the nature of the current, whether the supply is AC or DC. Next, you need to know the number and type of conductors. For example, on an AC system you may have active or phase conductors, a neutral conductor, and a protective earthing conductor. On a DC system, you will have equivalent conductors for that system. You must also know the supply voltage and its tolerance. For low-voltage systems in New Zealand, the nominal value is 230/400 volts, with a tolerance of +6% and -6% in the 2007 edition of AS NZS 3000. You must also be aware of regulatory changes. From about late 2025, the allowable network voltage range under amended ESR requirements has been widened to around ±10%. So the designer must always check the current ESR rules. Those voltage and tolerance figures affect both the equipment you select and how the circuits are designed. You must also know the frequency and its tolerance, typically 50 Hz, along with the allowable variation. Another important point is the maximum current that the supply can provide. This tells you how much load the installation is permitted to draw. You also need to know the prospective short-circuit current at the point of supply. In practice, this value is usually supplied by the electricity distributor. It tells you how high a fault current the protective devices and switchgear must be able to withstand. Next, you look at the protective measures built into the supply system, for example, whether the supply uses an MEN earthing system. You must also find out any limits or conditions set by the supply authority, such as maximum demand limits, starting current limits, or power factor requirements. Lastly, you need to be aware of any limits on harmonic currents or other power quality issues. If the distributor has rules about harmonics or voltage disturbance, your design must comply with those limits. In summary, before you design the installation, you must fully understand the supply, its voltage, frequency, fault level, earthing system, and any conditions imposed by the distributor. Clause 1.6.3, Maximum Demand. The next step is maximum demand. The designer must work out the maximum current the installation is likely to draw under normal use. To do this, you consider the total electrical load, how the load is distributed through the building, and how the equipment is expected to operate. Once the maximum demand is known, the consumer's mains, submains, final subcircuits, and all other relevant parts must be sized so they can carry that current safely. In simple terms, the installation must never draw more current than the supply, the cables, or the switchgear can safely handle. Clause 1.6.4 Utilization voltage. Utilization voltage is the voltage that actually arrives at the equipment. The installation must be designed so that, during normal operation, the voltage at each appliance or item of equipment is suitable for that equipment. To achieve this, the designer must consider voltage drop along the cables, the length of the cable runs, the loading on the circuits, and the supply tolerances discussed earlier. The standard refers to Clause 3.6 for the detailed voltage drop limits. It also notes that standalone systems must keep the point of supply voltage within the range given in Clause 1.6.2 subclause C during normal full load conditions. In simple terms, even when everything is switched on, the equipment must still receive a voltage that falls within its proper operating range. Clause 1.6.5 Electrical installation circuit arrangement. Finally, we look at circuit arrangement. The installation must be divided into circuits in a way that avoids danger, reduces inconvenience when a fault occurs, and allows safe operation, safe inspection, safe testing, and safe maintenance. This means you do not put everything on one circuit. Instead, you divide the installation logically so that one fault does not shut down the entire building, and so that parts of the installation can be safely isolated for maintenance. The detailed rules are given in Clause 2.3, and those requirements must be followed. In simple terms, circuits must be arranged so the installation is easy to control, easy to fault find, and safe to work on, and so that a single fault does not take everything out. Section 1.7 Selection and installation of electrical equipment. Clause 1.7.1 Essential requirement. When we choose and install electrical equipment, the standard gives one clear message. The equipment must be safe, must work properly, and must be installed the way the manufacturer intended. This means three things. First, the equipment must operate safely and reliably during everyday use. Second, it must not introduce danger, not electric shock, not fire, not overheating, and not physical injury, even when unusual conditions occur, such as an overload, a fault, or unexpected environmental conditions. And third, the manufacturer's installation instructions must be followed exactly. No shortcuts. In simple terms, choose equipment that is suitable for the job, install it correctly, and make sure it stays safe whether things go right or things go wrong. Clause 1.7.2 Installation Work Practice. To meet those safety requirements, installation work must follow good, safe practice. The standard highlights several key considerations. First, the equipment must be suitable for the environment. It must cope with the temperature, weather, mechanical forces, or any other environmental conditions where it is installed. Any built-in protection must still work after installation, and extra protection, such as an enclosure, must be added if needed. Second, the manufacturer's instructions must always be followed. Third, enough space must be provided for safe operation, inspection, testing, and maintenance. Fourth, mechanical fixings must be strong enough. Brackets, screws, and supports must hold the equipment securely and remain durable over time. Fifth, the design must consider the needs of the user and how they will operate the installation. Sixth, wiring colors must comply with the rules. Green, yellow, or green/yellow are only for earthing conductors. They must never be used for active or neutral conductors. Seventh, socket outlet polarity must be correct and must be consistent throughout the installation. And finally, semi-enclosed rewirable fuses cannot be installed. They are not permitted. In simple terms, install equipment safely, mount it securely, wire it correctly, follow the instructions, and ensure the installation suits its environment. Clause 1.7.3 Equipment Selection. When selecting equipment, it must meet the essential safety requirements in the standard. The standard says equipment is acceptable if it meets at least one of the following pathways. 1. It complies with AS/NZS 3820, the General Safety Standard for Low Voltage Equipment. 2. It complies with a relevant technical standard. This may be an Australian standard, a New Zealand standard, or a joint AS/NZS standard for that specific type of equipment. If no suitable AS/NZS standard exists, a recognized international or national standard from another country may be used, provided it is appropriate for the equipment and for the installation conditions in Australia or New Zealand. 3. The equipment carries the RCM mark, confirming it meets the required safety regulations. 4. In some cases, regulators may accept other recognized marks or evidence of safety. In simple terms, select equipment that complies with the correct standards or recognized safety approvals, and make sure it is appropriate for the installation. Clause 1.7.4 Damp situations. If electrical equipment is installed in a damp or wet location, the risks increase and so do the requirements. The equipment must be selected and installed so that it operates safely around moisture, reduces the risk of electric shock in wet environments, and avoids damage that could reasonably occur due to damp conditions. In simple terms, in wet or humid areas, choose equipment designed for those conditions and install it so moisture cannot compromise safety. Section 1.8 Verification, Inspection and Testing. Before any installation is put into service, whether it is new, extended, altered, or repaired, it must be inspected and tested. This is not optional. The purpose is to confirm that the work complies with the standard. Inspection and testing must be carried out as far as practicable, meaning as thoroughly as site conditions allow. During this process, precautions must be taken to avoid danger to people and damage to equipment or property, alterations and extensions. When modifying an existing installation, you must confirm two things. 1. The new work complies with the standard. 2. The new work does not make the existing installation unsafe. In simple terms, when you add wiring or equipment, make sure you are not introducing hazards into the older part of the installation. Correct conductor connections. Verification also includes checking that all conductors are connected correctly, especially to protective devices, switching devices and control devices. This ensures that fuses, circuit breakers, RCD devices and switches will operate as intended. Reference to Section 8. Section 1.8 tells you what must be done. Section 8 provides the detailed procedures and tests, essentially, how to do it. In simple terms, Section 1.8 says test it, and Section 8 says here is how you test it. Section 1.9 Means of compliance. Section 1.9 explains the pathways that can be used to show that an installation complies with the standard. This is particularly important for special designs, alterations and additions. Clause 1.9.1 and Clause 1.9.2, Australia only. These pathways apply only in Australia and are not used in New Zealand. Clause 1.9.3, Alterations, Additions and Repairs. Whenever you alter or add to an existing installation, the new work is treated as if it were a new installation. This means the full requirements of the standard apply. If the original installation was built using a Part 1 design, the new work must not reduce its level of safety. When altering an installation, the new work must not carry currents or voltages above what the standard permits, and it must not be used in a way that is non-compliant. Repairs may use similar methods or materials to those originally installed, but only if the repaired part still meets the fundamental safety principles of Part 1. In simple terms, all new work must be safe, must comply with the standard, and must not make the existing installation unsafe. Clause 1.9.4 Compliance by specific design and installation. Sometimes an installation has unusual requirements and cannot follow the usual Part 2 methods. In these cases, the designer may create a specific design based on the principles in Part 1, but this is only allowed under strict conditions. Clause 1.9.4.1 Using a Part 1 design solution. A designer may use a Part 1 design if they can show that the installation meets the fundamental safety principles of Part 1, that the level of safety is at least equal to what would have been achieved using the normal Part 2 methods, and that all other relevant requirements of the standard are satisfied. Any portions of the installation that are not part of the special design must still comply with Part 2. In simple terms, a special design is allowed, but it must be just as safe as a standard installation. Clause 1.9.4.2 Acknowledgement by the owner. If Part 2 is not being followed, the owner or operator must formally acknowledge this departure. This ensures they understand and accept the design approach. Clause 1.9.4.3 Documentation. The designer must fully document the design. The documentation must explain why the usual Part 2 method was not used, specify the verification steps required to confirm compliance, show how Part 1 requirements are being met, include the owner's written acknowledgement, describe any special installation methods, and record the tests and inspections carried out. The documentation must be kept by the designer and also kept on site by the person responsible for the installation. In simple terms, a special design must be fully documented, and the owner must agree to it.